We are continuing with series, and we will discuss a variety of tests to figure out if a series converges or diverges. Now, what have we done so far? So far, we discussed the definition, right? We take a series, you add up to index n, so from maybe 1 to n, the terms. This is Sn, the nth partial sum, and this forms a sequence. If this is a convergent sequence, then the limit as n goes to infinity of Sn, this is the sum of the series. And if the partial sums, the sequence, if the partial sums as a sequence, if they diverge, then the series diverges. But I also mentioned, typically, it's very difficult to get our hands on the partial sums, to get our hands on Sn in some closed form where we could actually evaluate a limit. Okay, we were able to for telescoping series, geometric series, and then we talked about the term test, which is not too hard to use, but it's very easy to misuse. So if the terms go to 0, as we discussed, term test tells you nothing. Okay, well, then I also brought up the harmonic series at maybe the end of the last video. I brought it up without saying why it diverged, but I mentioned it did. But it's an example where if you look at the terms, you see the terms are 1 over k. The limit as k goes to infinity, 1 over k, 0. The terms go to 0, but the harmonic series, as we will see momentarily, this diverges. And it's an important example because of this. Okay, well today, we are beginning with non-negative series. So we will have a number of tests with non-negative series. And this is one of them. So for example, what is a non-negative series? It's one where the terms like this are non-negative. Okay, we don't see a -1 to the k or even a sign of k over something because the sign can be positive and negative, for example. Okay, this is a non-negative series. Okay, well, here we go. Let's first talk about the harmonic series and how is it related to this picture. What you see here looks like, well, hopefully to you, it looks like Riemann sum, right? And it really is. So what am I going to do here? What I can do for this series is I can represent Sn, which is the sum k equals 1 to n of 1 over k graphically as a partial sum. Oh, excuse me. It is a partial sum. I meant Riemann sum. So many sums. A Riemann sum for f of x, maybe I should write that, for f of x is 1 over x on 1 to n plus 1. And in particular, we see the Riemann sum I'm discussing here. In particular, it is a left Riemann sum. I didn't specify that, but it is. Okay. Now, why is this Riemann sum literally this partial sum? Well, here, okay, this we have in this picture, delta x, we see for my Riemann sum is, maybe I'll write this in blue, we see here delta x is 1 in my picture. Okay, and this height, well, it's the function value at 1. This height is 1. The height is 1. This height is the function value here, a half. This height is a third. This height is a fourth. This height is a fifth, right? Just looking at the function value at 5. Then, of course, I can't draw all the way out to n, so I just put these dot, dot, dots. This height of this last rectangle is 1 over n. Okay? We see here, this Riemann sum, if we write out what it is, well, the area of this rectangle is, well, base times height. The base is 1. It's our delta x for this Riemann sum. This area is 1. This area is, well, 1/2 times 1, 1/2. So So each area, this area is 1. This area is 1/2. I look like I'm writing the function value, but I really am because my delta x is 1. This area is 1/4. This area is 1/5 all the way out to this one, which is little. It's 1 over n. We see, that Sn, this now I'm referring to my partial sum, Sn, okay? Which is just adding up these numbers. Well, look, all of this is above the function, above the function, above the function, right? This left Riemann sum is definitely bigger than, well, the area under here is more than the actual area under the curve. So Sn is greater than the integral from 1 to n plus 1 of 1 over x dx. This is what we get by this representing it graphically as a Riemann sum, as a left Riemann sum in particular. We see that this partial sum is bigger than this definite integral. Now, what are we going to do? Well, by definition, we take a limit as n goes to infinity of Sn. This is going to tell us whether or not this series converges or diverges. Okay, so you are bigger than, well, what happens when we take a limit? If we take a limit as n goes to infinity of this, well, this is an improper integral, right? Not written exactly how we saw it. We had as b goes to infinity and would be 1 to b, right? But it's basically the same thing. But this here is, I will do it exactly, a limit as n goes to infinity. We integrate ln absolute value of x. This would be ln of n plus 1 minus ln of 1. Of course, that's 0. Now, as n goes to infinity, natural log grows without bound. So this is infinite. Now let's go back to think about my series, or my partial sum of my series. This is bigger. Sn is bigger than something, right? This is with respect to n. This is with respect to n. Sn is bigger than something that as n grows, this side is growing without bound, okay? We're bigger than something growing without bound. What can possibly happen? Well, if you're bigger than something growing without bound, you are going to infinity as the only option. So we can conclude here that the limit as n goes to infinity of Sn is infinite, or we know d and e as a finite number. This says, just by comparing this partial sum to a definite integral, this says that this harmonic series diverges. Okay, so now we see why the harmonic series diverges. Okay, by thinking about the continuous function 1 over x. And this is not just something special to the harmonic series. This notion and this discussion really generalizes into a test that I will mention right now. And you can imagine the name is called the integral test. Okay, so let me erase this. And then I will write the integral test, and we will do some examples, and it will also lead us to another named series I mentioned last time called the PSeries, which is an important, very important series that we use. Okay, so the integral test. Okay, well, every single test we learn has some hypotheses, and you have to make sure that whatever series you're using satisfies them, otherwise you can't use the test. So for the integral test, we suppose f of x is we need three things. We need continuous, we need non-negative, maybe I'll write decreasing because I think that's shorter, but that was the third thing. We need continuous, decreasing, and non-negative. Decreasing and non-negative on 1 to infinity, and let's say AK is f of k. Okay, so you have a function. So what this says is, well, let me write the conclusion, then we'll talk. So the statement is then the sum k equals 1 to infinity of AK. And this improper integral, 1 to infinity f of x dx, this is what we just had, right? We had f of x was 1 over x, and we had the sum of 1 over k. That's this statement, and that was what I was starting to say. You have some function evaluated just at the integers. This gives you your series. Okay, so then the series and the improper integral, they either both converge, or both diverge. Okay, so the thing is, series, very difficult to get our hands on SN explicitly. It's closed formula, for example, but, well, integration is sometimes quite hard, but we have definitely practiced improper integrals. So if you have some series and the terms, you see a continuous, decreasing, non-negative function, then you can think about integrating. And if you can integrate the function, for example, the improper integral will converge precisely when the series converges. The improper integral diverges precisely when the series diverges. But let me make this important comment that the value of this sum or I should say the values, because there's two different things here, the values of the sum and the improper integral, they are not the same. They will not be the same when in the convergent case. So when you're in the case, and this is important to understand, when you are in the case that both series converge, it's not the case that you know the value of this integral, I don't know, say it's 5, that the sum is 5. It doesn't work like that. In fact, I'll mention an example where we know the sum of the series from a famous mathematician. It's not like it's easy for us to calculate. And we can also see the value of the integral, and we will see they won't be the same. Okay. You can get bounds, for example, on this, using this, but we won't get into that so much this semester. As I mentioned in the last video, we calculate the sum for geometric series. We calculate the sum for telescoping series. And that's really about it. Okay, everything else we just use tests to figure out if it converges or diverges. Okay, well, maybe let's do a short example here. And this will I will do this because I was just thinking, this is the one that I can say something about. The sum 1 over x squared. Well, this is a special case. I'll write this here. This is a special case of something called a P-series, which I will mention right after this. Okay? We will see this as a P-series just in a moment. But you notice, oh, this should be a K. My apologies. I was writing it in the continuous function notation. Okay. You notice here, now I have the series written correctly. Here, okay. Well, you notice if you take f of x is 1 over x squared, this is continuous. This is non-negative. And because the denominator is growing without bound, this is decreasing. Okay? So we may use the integral test, which says we integrate 1 to infinity, 1 over x squared dx. This is a limit as b goes to infinity, the integral 1 to b of x to the minus 2 dx, a limit as b goes to infinity of, well, we add a power, divide by the higher power. It's going to be an x to the minus 1 over minus 1. Or like this. X to the minus 1 over minus 1 is here, evaluated 1 to b equals the limit. I might run out of space actually. Here, which is as we go to infinity. Well, this part goes to 0, and so we get 1. Now, I'm going to continue this up here. My apologies for moving mid-problem, but I ran out of space. Okay. So let me continue this problem up here. So we will continue. I'll recopy the series. And then I'll just write, well, we've calculated this integral. So I will say as this integral, 1 to infinity of 1 over x squared dx, as this is 1 by the integral test, integral test, the series k equals 1 to infinity, 1 over k squared converges like this, okay? Because the integral test has the same behavior, right? And we need to check, as I mentioned, that you have a continuous, non-negative, decreasing, okay? You need to have all of those. We do with this function. Then the integral test says that this improper integral has the same behavior as the series, namely it either converges or diverges. They both have the same. Okay, well, this is one. This is a comment. Is that Euler proved that the sum 1 over k squared is pi squared over 6, okay? And so just in this example, of course, I'm not going to calculate this. I'm not even sure what went into the proof. That might be interesting to think about. But the point of this is, you see, these two are not equal, and it will never be the case that the integral, improper integral, and the series of the corresponding, where you take ak is f of k, they don't have the same value. Okay, that was just a comment, and it's a little bit interesting to think about. Now, let me now define P-series, which we will see this one is a type of P-series, and we will discuss when the P-series converges and diverges. Okay, so what is a P-series? Maybe I'll put a line. The P-series. Okay, well, P-series look like this. K equals 1 to infinity, 1 over k to the p. Okay, let's write out some terms, because I would say I see a lot of mistakes where people will confuse geometric series and P-series. So let's take a moment. Is it versus or versus? Maybe I'll put VS. I'm not sure which spelling to use here, so I'll put versus the geometric series, because I'd like to see them together and really take the time to realize that these are fundamentally different series. And this, well, both of these, you don't have to start with this indexing, but looks like this. Okay, so let's write out some terms here. Okay, well, this would say 1, well, okay, I'll say 1 over 1. I'll write it like this, to the p, plus 1 over 2 to the p, plus 1 over 3 to the p. plus 1 over 4 to the p plus 1 over 5 to the p, okay? Like this, where p is some number, okay? This is a plus ar squared plus ar cubed plus ar to the 4th, ar to the 5th, etc. You see, these are very different. Here, the power that you see remains the same. It's p. But what changes is what you're raising to the power is marching up by the integers. Whereas here, the power is sort of what's varying, right? You have this ratio. As you move from one to the next, you're multiplying by r. This is what gives you geometric series. If you move from one to the next, and every single time you're multiplying by the same number, you are geometric. And you don't see that here, right? Definitely not. As you move from one to the next, even take p equals 1, which is the harmonic series, then this is 1 plus 1/2, 1/3, etc. If you take p equals 2, this is 1 over 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, like this. These are fundamentally different, and understanding which one you have is an important thing. Just spot a p-series, spot a geometric series immediately, and be able to say when it converges, when it diverges, like this. Okay, well, p-series, geometric series. Okay, now let's talk about when the p-series converges, when it diverges, and I will do some examples where I verify it, but I won't prove it generally for p, although you certainly could. Okay, so the p-series here, this converges when p is strictly bigger than 1, and it diverges every other time when p is less than or equal to 1. Okay, and this, just to refresh your memory, this converges when absolute value of r less than 1, and it diverges when absolute value of r bigger than or equal to 1, like this. So if you were ever handed a p-series, handed a geometric series, your justification is you just state it's a p-series, you state what p is, either that it's bigger than 1 or less than or equal to 1, and then the conclusion, converges or diverges, like this. Most of the series we will be handed, you'll have to use p-series, geometric series somehow. Potentially you might, but it might be a little more complicated than just one p-series, for example. Okay, well, what have we seen so far? Let me erase this justification. We have seen 2 p-series, and then I will do some more. We've seen this one, and we've seen this one. This is a p-series where p equals 2, bigger than 1, converges. Okay, I already showed this with the integral test. In fact, that's how you show most of them. Well, as long as, let's see, p is 0, you're just adding up 1. Okay, as long as p is greater than 0, you can use the integral test. If p is less than 0, well, think about it. If you have a negative number, it's really up here in the numerator with a positive exponent. You could use term test to see that it diverges. I'm in this case. But any p positive, you can use the integral test to prove either that it converges or diverges. Here we already showed, right? But if you were given this in the future, you can just quote that it's p-series, as I mentioned. And this one, well, this is a p-series where p equals 1, which is less than or equal to 1, here, diverges. But the justification that you would need in the future for a harmonic series diverging, you can either just say this is the harmonic series, it diverges, or you can say it's a p-series with p equals 1. Those are both valid arguments. Okay, now, of course, this in blue, unlike the geometric series where I justified it, I didn't justify, but let's do a few more examples of the p-series, And I might do one, yeah, let's do at least one where I justify with the integral test, like this. So let's look at some more P-series. Let's look at the sum, k equals 1 to infinity of 1 over, let's say, the cube root of k. Okay, this is a P-series. And why is it a P-series? Well, it's a sum, k equals 1 to infinity of 1 over k to the 1/3. Okay? Now, if you're handed this on a quiz, exam, whatever, you can just quote the P-series test. You can just say P is 1/3 less than or equal to 1, P-series diverges like this. But I mentioned I want to actually justify it because I didn't justify the P-series test per se. So let's use the integral test here. We're trying to also practice this test. Okay, how would we use the integral test? Well, my function f of x is 1 over x to the 1/3. This is, without a doubt, all of the adjectives. It's continuous. Continuous. It is non-negative. And because the denominator is growing, fixed numerator, it is decreasing. And all of this on 1 to infinity. Okay, so I may use the integral test. Okay? So then if I integrate 1 to infinity of, this is an x to the minus 1/3 power, excuse me, this is a limit as b goes to infinity, the integral 1 to b. Make sure every time you use the integral test, if you are computing an improper integral, you have to write the steps of the improper integral. I've seen students that think, well, I'm working on series now, and so they just shortcut and they don't write the fact that an improper integral is actually a limit, but it is. So you have to show your work. This is the definition of an improper integral, as you hopefully recall. Okay, then, well, this is a limit, and then we add a power, which this is going to be a 2/3 power, evaluated from 1 to b. I keep doing my integral test so low I run out of space. Okay, well, this is all right. We will finish this. Okay, it's going to be 3/2 b to the 2/3 minus 3/2. 1 to the 2/3 is just 1. Now, you see, b is growing without bound. If you raise something to the 2/3 power, this is what, the cube root of b squared, for example, this is going to infinity. So this integral is infinity, or does not exist as a finite number. Okay, so the only thing you'd have to do to finish the problem, which I will write at the very top, okay, to finish this problem, maybe I should erase this too because it's no longer relevant with the P-series erased off the board, but to finish the problem, we just say, well, by the integral test, we see this series, k equals 1 to infinity. Oh, maybe I'll write it as it was handed to us, diverges. Okay? Now let's do this example, and this is, well, this is not a P-series. It's not geometric series. It's not telescoping. Well, if you look at the terms here, 2 over k times ln k to the 6th, the terms go to 0, so you can't use the term test, but this is a very nice series for the integral test. So if we consider f of x to be 2 over x ln x to the 6th, okay, then This function is, well, what do we need for the integral test? We need continuous, decreasing, non-negative. And in fact, it is, right? This is definitely continuous. This is decreasing. And this is non-negative on, well, here, and I will say this is a little bit different because we see the sum starts at 3. Okay, I'll put 3 infinity. I could have started this sum at 2, but you notice I cannot start the sum at 1 as we've seen in many other examples because at k equals 1, the natural log of 1, 0. And so my series is undefined at 0, at 1 because you can't divide by 0, right? But, okay, this function is continuous, decreasing, non-negative. We may use the integral test. Okay, so we need to compute the integral from 3 to infinity of 2 over x ln x to the 6th dx. This is a limit. As b goes to infinity, the integral 3 to b of 2 over x ln x to the 6th. Okay, well, if you look at this integral, substitution, right? Because here we see inside parentheses, we see a log. And then we have a multiple of its derivative because the derivative of natural log 1 over x dx. So let's do the work over here. U is ln x. du is 1 over x dx. We have 2 over x dx, which will be 2 du. Okay? Then, well, me personally, you know I changed my bounds. Here we go. So when x equals 3, u is ln 3. When x equals, oops, I almost misread that and put 6. B, u is ln of b. Okay, now I will put all of this in a little box and we will integrate. Very nice. This becomes, well, we have a limit as b goes to infinity, but now I change everything to be with respect to u. So my integral goes from ln 3 to ln b, and then I have 2, let's see, no, we have 2 du, and then we have, u to the minus 6, very nice, times 2 du. Okay, now here we go. We integrate. These are fun, I think. B goes to infinity, the integral, we have ln, now we integrate. We already converted to an integral of u, so we add a power, divide by the higher power, evaluated between ln 3 and ln b, and then I will give myself a little bit more space. Because I will be taking a limit, I'm going to move things, like I will move this -5 into the denominator with a positive exponent. So this is minus 2 over 5 ln b to the 5th. Then minus a minus becomes plus. We have plus 2 over 5. We have ln 3 to the 5th. Okay, well, this is some number, right? I don't have a calculator up here, but it also doesn't really matter. The only thing varying with b is this part. I mean, the particular calculator number of this doesn't matter, right? There's no b in it, so I can evaluate the limit, and this has the b. Now, as b goes to infinity, the natural log grows without bound, and well, in particular, the natural log to the 5th will grow without bound, but it's in my denominator. So this term is going to 0. And then we take the limit and we have just, okay, I think I have space. The limit is 2 over 5 ln 3 to the 5th. Okay, now, well, what does this say? It says the improper integral converges. In fact, this is the value. Now we can use the integral test. Well, we've been using it, but I will quote it. By the integral test, my series, maybe I'll use a little bit more space. I'll go down a line. K equals 3 to infinity of 2 over K ln K to the 6th converges, okay? Because the integral test says, that the improper integral and the series have the same behavior. And we show the improper integral converges. It's this number, finite, and therefore the series by the integral test does too. Let's do a few examples. Let's see, sum K equals 3 to infinity of, let's do K to the minus 4. We will do a sum. K equals 2 to infinity. Let's say the square root of K plus K over K to the 5th. And then we'll do one more. Now, none of these am I going to integrate, okay? I might do one more that I integrate at the end. We will see. And then let's do, I'll even start at something different, 3. Let's do 1 over 2K cubed. Okay, what can we say about these series? So I told you I wasn't integrating any of these. I'm just going to use, well, in all of these, I'll just use PSeries, and I'm going to use properties of how series work, which is a good thing to think about. So first of all, with this first example, what do we see? It's not handed to us looking like a PSeries, but it really is. If we rewrite this, this is the sum, K equals 3 to infinity of 1 over K to the 4th. So this is a PSeries where P equals 4. This is strictly bigger than, oops, well, it is bigger than 2. I meant to write bigger than 1. This means it converges. Now, starting at 3 versus starting at 1, it doesn't really matter, okay? In fact, generally with series, and I think you might have worked some problems like this, or you will be soon, there might be a question like this. If you know, if you have this, let's say K equals 1 to infinity of AK. And then if you want to compare the sum, the same thing, 6 to infinity of AK, okay? And the question is converge or diverge. Well, both of these will either converge or both will diverge, okay? Assuming that these AKs are the same. I mean, this is one little example here. And it's related to this where I just took a PSeries as we're used to, where you start at 1 and I start at 3 instead. Okay, so why do these have the same pattern of convergence versus divergence, or divergence I should say? Well, what's the difference here? The series on the left is A1 plus A2 plus A3 plus A4 plus A5 plus this series, right? This is the only difference between these two series. And this one, well, we don't know exactly what it is, but whatever you do, you take 5 numbers, add them up, it's a finite number, right? Take any 5 numbers, add them together, you have a number. So really, these two, if this converges, this converges. If this diverges, this diverges. And this is one reason why, if you're only specifying convergence or divergence, where you start really doesn't matter, because what governs a series converging or diverging is the infinite tail, what's happening sort of as you go to infinity. Because you could even take the first 10,000 terms, finite number, okay? Okay, that was my sort of comment. We should see it in a worksheet sometime soon, if you haven't already. Okay, now, we have discussed this first one. This is a P-series convergent. This, as written, is not a P-series exactly, but we may break this, and we did an example like this in yesterday's, or maybe, I don't know when you watched it, the last video. We may break this into a sum. We would have square root k over k to the fifth, and then a sum of k over k to the fifth. And then I can simplify each of these properties of exponents. This first one, this is, well, this would be a 5 minus a half, would be 9/2. This is a k to the 9/2. Okay, and then this one is k to the 4. So we see here, this one, this series here is the sum of two convergent P-series. Well, the first one, maybe we have P is 9/2, bigger than 1. And the second one is P equals 4, bigger than 1, like this. And if you take, well, this is properties of convergent series. If this sum is a number and this sum is a number, which it is, right? This will converge to this number plus this number, like this. So this one will converge. It's the sum of two convergent series. And this was my sort of justification as, oh, not k, P equals 4. Okay, bigger than 1. Okay, so far we have converges, converges. Okay, maybe I should have done an example where they diverge. But in any case, maybe I'll do that next. Okay. Here, now this is also convergent. Oh, let's change it, make it divergent. Just because, as I mentioned, I did two that converged. So how can I change this to make it divergent? Let's raise it to the 0.8 power, okay? So now we will have, I'm going to be talking about the exact same property of series, but at least we have an example of divergent. Okay, well, what can we do here? Let's use properties of exponents. This would be k equals 3 to infinity of 1 over, we have 2 to the 0.8 times k to the 0.8. Right, that's just properties of exponents, where this is some number. And now that I've changed it from 3 to 0.8, I don't know what this is exactly, right? But it's a number, which is all that matters. What this is, well, as a comment, if we didn't have this part, the 2 to the 0.8, we do know that this, just 1 over k to the 0.8, diverges because it's a P-series and P equals 0.8 less than or equal to 1, okay? But then I take this and I multiply this by a number. Each term multiplied by the exact same number. I'm multiplying the whole series by a constant. Well, what can we use here? This is really a if and only if thing I will mention. We can use this. And this comes up quite a lot and is worth discussing. This, so I'll write it. If you have a series And I'm not going to even write the k equals something to infinity. You will see this in the text sometimes. They just write like this for a series. So this series and this, well, let's say c is not equal to 0 is a constant, because 0 is a different situation. Then this series and this series, they both converge or both diverge. Or I could say this series converges if and only if c of ak. So this converges if and only if, I'll write it, if and only if this with a c, you multiply here, ak, converges. Now what is this? This is really using, it comes from properties of limits, and we know that the sum of a series is really a limit of partial sums. But in any case, what this says is, if you have a convergent series, you multiply by a constant, it's going to converge. But it's an if and only if. So that also says if you have a divergent series, multiply by a constant, it will diverge. Okay, so how would I justify this? Well, what I would do here, this was a side comment now that we have discussed this. The way I would justify this series, I would say this diverges as it is a constant times a divergent p-series. P-series. And then I would say p equals 0.8 less than or equal to 1. Okay, so that is justification. Now I can erase this because it's fully justified below. That's justification here for why this series diverges. It's a constant times a divergent p-series. Okay. Okay, now let's do another, maybe one more, I think. Yeah, we'll do one more example of the integral test. Let's look at the following series. Let's say, I'll do n, why not? 1 to infinity of 3 over n squared plus 1. Now, you know, we are going to learn a variety of tests. It's definitely not the case that everything you see is a p-series or a geometric series or a telescoping or integral test or a term test. That's what we have so far. That seems like a lot, right? But it's not the case that you can use the integral test for everything. For example, even before I start this problem, here's an example. And we will see next time a very nice way to figure out that this is a convergent series. Well, there's multiple ways we can figure it out, but in particular, my point at the moment is we cannot use the integral test. And this is my comment right now. We cannot use the integral test. It's always good to know, for example, when you can use a test and also when you cannot use a test. This one, we cannot use the integral test. Certainly this function is non-negative. Certainly this function is decreasing. Well, as we move from k to k plus 1 to k, from 1 to 2 to 3 to 4 to 5, this is decreasing because k factorial grows. But it's not continuous. So this k factorial, anything with factorials, not continuous. I mean, they're not even, the factorial function is not even defined on the whole real line. You can't integrate it. Okay, this would be an example that you cannot use the integral test. Okay, now, one reason I brought that up is because this one, which without a doubt we can and will use the integral test, for me personally, after starting next video, I wouldn't use the integral test on this. Okay, so I bring up this fact that we will see more tests just because sometimes, like this one, even though you can use a variety of tests, I wouldn't use the integral test, but I will today because we're still learning. And as of today is all we have. Okay, so my function. This is without a doubt continuous and decreasing because again, the denominator is growing, right? Fixed numerator, and it's non-negative. All of this is true. And I need this to be the case on 1 to infinity, and it is, okay? So we may use the integral test, and we evaluate this. This is a limit as b goes to infinity, 1 to b, of 3 over x squared plus 1 dx. This is, well, this we have integrated multiple times this semester. Here it is again. This is the inverse tangent. So we have 3 tan inverse of x evaluated from 1 to b. And then we have a limit, oh, I think I'm okay here. B goes to infinity of 3 tan inverse of b minus 3 tan inverse of 1. Okay, then, well, this tan inverse, as you go to infinity, goes to pi over 2. This term will go to 3 pi over 2. Okay, now, tan inverse of 1, what angle between minus pi over 2 and pi over 2 has tangent 1? This says the sine and cosine are equal. Pi over 4. So this one, well, this is 3 times. Maybe I won't circle it because it's not a limit. We just evaluate, so I will do that in the next step. Okay. So then, this integral is 3 pi over 2 minus 3 pi over 4, which is going to be 3 pi over 4. Okay, which is convergence. So this improper integral converges by the integral test. My series n, I have an n here, to infinity of 3 over n squared plus 1 converges. Okay.